I'm pleased to introduce today's session, Introduction to Multilingual RAG, and our guest speaker, Yujin Tang. Yujin has a background as a software engineer working in auto ML at Amazon. He studied computer science, statistics, and neuroscience with research papers published to conferences including IEEE Big Data. He enjoys drinking bubble tea, can confirm, spending time with his family, and being near water. Welcome, Yujin.
Thank you, Emily. Yes, I love bubble tea. Okay. Hello, everyone. My name is Yujin. Today we'll be talking about multilingual RAG. So I'm currently a senior developer advocate at Zillis, and this slide is basically for you to find different ways to contact me. The best way to contact me is through LinkedIn, which is available through the QR code there on the right-hand side of your screen. As Emily was saying, my background is in software, working on machine learning. I did a bunch of research in machine learning, published some papers, and I've been working in NLP since 2021. And I've been building a lot of RAG apps and AI agents over the last year or so. And today we're going to talk about how you can build multilingual RAG, which is RAG on different languages. So the contents of our talk today, we'll start with a RAG review, just a review of what RAG is. This will be a short commentary on different RAG topics, and then we'll go into LLMs and embedding models. So we'll cover a short history of LLMs and compare them to what embedding models are. This is something that came up a lot last year in my talks. People were asking a lot about the differences between LLMs and embedding models. So we're going to talk a little bit about these differences. Then we're going to talk about vector databases. Vector databases are critical to building RAG applications. And then we're going to go into the demo. So the primary reason that you would use RAG is basically because you want to inject your data. You want to inject your data into an LLM, right? So when you're working with an LLM, you're typically working with some sort of generalized model, and it doesn't have access to the data that you want it to have access to, or that your private data is generally not going to be used to train an LLM. And so in order to get an LLM to work on your data, you need to use RAG, which allows you to do this kind of factual recall. And it's also good for cost optimization because you can kind of pull your context in and you can play around with your context windows and how many tokens you're using and all these kinds of things. And this is really important for production. So this is a general picture of a RAG model of a RAG setup, right? So we're going to start at the bottom left-hand corner where it's your data. And basically in a RAG setup, you take your data and you put it into an embeddings model. You run it through an embeddings model. The embeddings model will generate vectors, and those vectors will go into a vector database like Milvus. And then at query time, when you actually use your application, your query goes to an LLM. The LLM decides what needs to be searched in the vector database, and then it sends that search once again through an embeddings model, which will turn that the text of that search into a vector. And that will go to a vector database like Milvus, and it will search Milvus for some vectors and then return those vectors to the LLM along with the metadata, which includes the text. And that is how the LLM is able to answer your question. So this is just a basic overview of RAG. That's really all we're going to cover there. Now let's go into some differences between LLMs and embedding models. So in order to understand the motivation for RAG and how it works, we should have some history, some background about LLMs. So LLMs started out, LLMs are a type of neural network, and neural networks started out back in the 70s, basically. The idea of which is that you're basically feeding in some numbers, doing a bunch of different calculations and getting some sort of prediction, some sort of regression, some sort of classification, some sort of output about that input, right? So this is a picture of a basic deep neural net. And essentially you take an input, which is going to be a series of numbers, you pass it through, you get some calculations going on, and then you pass out to a hidden, an output layer. And the output layer will give you some sort of prediction about your input. Now, as we evolved, I guess, as we worked on neural networks, as neural networks evolved, we began to see that there were certain types of neural networks that were really good for certain types of applications. So when it comes to text, when it comes to language, one type of neural network that we saw that was very helpful was a recurrent neural network. And the picture here is just one layer or neuron of a layer of a recurrent neural network. And you can see that when this is unfolded, what's going on is that you're taking inputs over time and reusing them. And so a recurrent neural network is able to keep track of tokens over time. And because it has this ability to keep track of this context, it is able to, because it has this ability to keep track of tokens over time, it's able to have some context and context window to look at text. But RNN still had a problem. It could only keep context so long, up to a certain length. And so in order to solve this problem, we introduced transformer models. So transformer models take an input, and essentially that input goes into some encoder, and the encoder creates a hidden state, a set of matrices, a set of vectors, whatever. And that hidden state then gets combined with, usually additional input is going to be an attention matrix. And so you take two matrices and you put them into a decoder, and the decoder will put out some output. So this was really helpful for us to basically solve this problem of short context windows. And this allowed us to have much, much longer context windows. Now, you'll still hear this as something that kind of is talked about in LLMs, is context windows, right? So some models have a context window of 8,000, some models have a context window of 4,000, some models have a context window of 1,000,000. And context windows are basically something that gets worked on by the way that the model is structured. And this kind of leads us to GPT, which is the state-of-the-art, one of the state-of-the-art models. And GPT uses a decoder-only architecture. And essentially what that does is it takes your sentence, your words, and it calculates a token and positional embedding, and then it outputs a predicted next token, right? So what GPT is doing is it's giving you a prediction for what the next token is most likely to be. So it is generating text, but that text is still a prediction, okay? And so basically in this example, what we're looking at here is if we take the chicken walked and we send it to GPT, it will produce across the road and then an end of sentence or a period. And what this is essentially saying is that if we give GPT the words the chicken walked, it's going to predict that the next most likely word is across, and then with the chicken walked across, the next most likely word is the, and again with the chicken walked across the next most likely word is road. And that would be the end of the sentence. And this is because it is predicting from the data that it has. So GPT is trained on a large corpus of data that's found online. And typically when you look online, you're going to see a lot of things about the chicken walking across the road as opposed to walking across anything else or walking anything else. So that's an LLM. But what about embedding models? Embedding models are the ways that we generate vectors. And you can really generate vectors from anything. You can generate vectors from any sort of unstructured data or structured data. So you can generate it from images, from videos, from text, from audio, from DNA examples. All of these kind of different things can be turned into an embedding. But the secret is that instead of doing the last layer of doing the prediction, right? Earlier, when we talked about neural networks, we talked about how neural networks will have a prediction at the end. Embeddings are the representation, the inner representation of some sort of data from a neural network. So as you pass data into a neural network, each layer is going to give some sort of calculation, and it's going to give you a quantifiable representation of that data. And that data is going to have a semantic meaning to that. So the last layer, the second to last layer of the neural network is going to output what the neural network has learned from that data without giving you some sort of prediction. And that's a vector. And that's what you put into vector databases to do semantic similarity search. So just to recap this section, LLMs are large models. That's why they're called large language models. They generate text via predictions. They have some sort of reasoning capability, or at least they seem to have some sort of reasoning capability. And the general architecture is based on the transformer architecture. Embedding models are smaller. They don't need to be based on transformers, and they do not generate any text nor give you any predictions. Essentially, you are taking the output of an inner layer of a neural network as your embedding. Okay, so let's talk about vector databases. Vector databases are meant to find semantically similar data. So if I give you these 3 sentences, Apple made profits of 97 billion in 2023. I like to eat apple pie for profit in 2023. And Apple's bottom line increased by record numbers in 2023. And I asked you to find which one of these sentences is, or which 2 of these sentences are most like the others, or most alike. What would you say? So this is an interactive presentation. If you think it's sentences 1 and 2, please put that in the chat. If you think it's sentences 1 and 3, please put that in the chat. If you think it's sentences 2 and 3, put that in the chat, right? So prior to vector databases, the way that search across text was done was through keyword search. And so keyword search, what you would do is you would look for specific keywords. And if I were to look for the examples of Apple, profit, and 2023, I would get back the first 2 sentences. But actually, oh, I see none of you guys have answered this question. Actually, the first and third sentences are the ones that are the most similar. Oh, wow. Okay, thank you. Yes, someone has answered the question. That's great. There's another interactive portion coming up on the next slide, so I hope you guys are ready. So actually, the first and third sentences are the most semantically similar. And so if you were to do search for the most similar sentences, you would want the first and third ones back. But if you were to do keyword search, as we would have done prior to vector databases, you would have gotten the first 2. So this is an example of something of how vector databases help. Now, it's not just text data that you can use this on. You can also use this on image data. So here I've got 4 pictures of one of my favorite artists and one of the most popular artists in the world. And the question that I have for you guys is, which one of these is the least like the others? So this one is picture 1. This is Taylor Swift 1. This is Taylor Swift 2. This is Taylor Swift 3. This is Taylor Swift 4. I would love for you guys to just take a guess. Which one do you think is the least like the others? Great. Okay. Everybody says Taylor Swift 2 is the least like the others. So I don't know if you guys have seen this presentation before. Maybe next time I'll split them up. Maybe next time I'll mix it up. But it is Taylor Swift 2. Taylor Swift 2 is the fake Taylor Swift. So this is just an example of how you, as a human, can do this kind of similarity comparison across the different pictures of people. But that's not actually something that is inbuilt into machines. And so in order for machines to be able to do that, they need to be able to compare things mathematically. And that's kind of how vectors work. Vector embeddings are long strings of numbers that allow you to mathematically compare things that are not, that we don't see as numbers. So this is an example of how that works. In this example of semantic similarity, we've got 4 words. We've got queen, woman, man, and king. And the idea behind this slide, if you don't take anything away from this slide, the only thing you need to remember from this slide is math on words, or math on things that aren't originally numbers. And the other thing that is incredibly important that I hope you remember to take away from this slide is that you see these words here on the first dimension. You see queen and woman and king and man have the same value along the first dimension. But this doesn't actually tell us what that first dimension means. It only tells us that these words have the same relationship on that dimension. So it doesn't, just because, you know, the first dimension is the same for queen and woman and king and man, it doesn't mean the first dimension means gender or sex or anything like that. It just means that those words mean the same thing on that dimension. So if we take this mathematical example, and keep in mind as well, this is a toy example. You will never see two-dimensional vectors in production, and you will never see people use Manhattan distance in production. We will talk later about some distances that you will see, but you'll almost never see Manhattan distance in production. So what happens here if we subtract the word woman from queen? So we have 0.3, 0.9 minus 0.3, 0.4, and we get 0, 0.5. And if we add 0.5, 0.2, which is man, we get 0.5, 0.7, which is king. So the idea behind this slide is basically math on words. Oh, we've got a question. What role does vectors dimensionalities have and how similar the data will be? Vector dimensionality is basically, I think you can think of it as a level of granularity in comparing similar data. But really, and we'll see this later on, what matters is not, what matters is, I mean, it does matter how many dimensions you have, but by the time you get to hundreds or thousands of dimensions, it's pretty similar. You start kind of like losing, what's that word called? It's like you get diminished returns as you increase dimensionality, right? What's actually important is the data that your models are trained on. Okay, so let's take a look at some of the similarity metrics that people do use, right? So we've just said that Manhattan distance is almost never used. So there are three types of distances that are used often in dense vectors. The first is Euclidean distance. This is L2. And basically what you're doing here is you're capturing the distance in space, the magnitude of the distance in space. So for those of you who have taken geometry, which I assume should be all of you, you will remember this thing called Pythagorean theorem, where you're essentially calculating a hypotenuse. You're calculating distances in space. That's basically the same idea behind Euclidean distance, right? If you draw this triangle here, if you're thinking of vectors as points and you're gonna draw this triangle here, then this is the distance between them as the hypotenuse. Okay, so that's one method. Next, we have inner product. So inner product is a little bit less intuitive, but it's actually very, very nice. It's a very, very simple, straightforward, and I say a very pretty way to get distance. So inner product is measuring the projection of one vector onto another. So in Euclidean distance, we would think of the vectors as points in space. In inner product, we think of the vectors as point with the line. And so when you project, you're getting a measure of both the magnitude as well as the angle, the orientation difference in two vectors. So that's inner product. Inner product measures the projection, and you can see from the equation that it is super simple, super computationally inexpensive. So next we have cosine similarity. So cosine similarity is inner product divided by the product of the magnitudes of the vectors. So it's a normalized version of inner product. And you would never use this unless you were using models that are specifically trained on cosine similarity. Why? Because it's more computationally expensive and it abstracts out the actual magnitude of the vectors. But cosine similarity measures the angle between two vectors, right? So we've just seen magnitude plus angle, and just the angle. So from this, you can kind of just think, what is actually more measurable, what has more degrees of freedom, degrees of granularity, and you will probably naturally come to the conclusion that inner product has the most degrees of granularity, and inner product or L2 are pretty much my go-to similarity metrics. Now, cosine is very popular and used a lot online. And the reason for that is because cosine was one of the first metrics that people started measuring when NLP started becoming popular in the late 2010s. But as many people tend to do, many people would use this measure blindly because of the popularity of the measure. And I would encourage you to make sure that if you're going to use a metric, make sure that it's the right metric for your embedding model. So just a review of metrics: Euclidean measures spatial distance, cosine measures orientational distance, and inner product measures both. And when you have normalized vectors, your inner product and cosine are the same. Okay, and now we've got indexes. So indexes are a way to access data. And this is really important because if you think about vectors, there are hundreds or thousands of dimensions. That's a lot of calculations to do. You want an efficient and effective way to do that. So some ways to do that include inverted file index, which is basically just K and N. Or sorry, K-means. It's a clustering algorithm, right? So what you're doing here is just finding clusters and centroids, and that's basically it. You're creating a Voronoi diagram. And so to create the index, you do a K-means, and then when you use the index, you basically search and look for the closest centroids, and then you retrieve all the vectors from those centroids and look for the closest vectors within those centroids. Next, we have hierarchical navigable small worlds, HNSW. And HNSW is a graph algorithm. And essentially what you do is you build a graph at build time, and then at search time, you go in and you search through pieces of the graph. So HNSW uses this thing called an exploratory factor, which is basically a cutoff for a uniform random variable. So if I were to use a uniform random variable of 0.9, then what would happen is every single at insertion time, at build time, every single vector would get inserted into layer 0. And then vectors above 0.9 would get layered into layer 1. Vectors above 0.99 would also be put into layer 2, and so on and so on. At search time, you start at your highest layer and you work your way down. So because this is a graph, the search is very fast. You have to do less computations to have the distance between the existing vectors. And it's also quite accurate because you're basically able to store all of these vector values quite easily. And now we're going to talk about the next two. We're going to talk about our quantization. So quantization you can think of as basically a bucketing algorithm, right? So if you were to bucket some data, if you were to take the real numbers and you return them in integers, that's an example of bucketing. That is basically how you can think of quantization. So instead of thinking of 0.0432, you would have 0. And instead of thinking like 7.1, you'd have like 7. Okay. So that's just what quantization is. And product quantization is scalar quantization across 2 dimensions. So not just across, let's say, the values within a vector, but also the values within a block of vectors. And basically, product quantization is able to compress much further, but it is not quite as accurate. Okay, so let's just overview the indexes real quick. So we have IVF, which is an intuitive index. K-means it takes a medium amount of memory. You're just holding the centroids, and it's pretty performant. And then you have HNSW, which is graph-based. It takes a lot more memory to do, but it's very performant. And then you have flat, which is a basic, I'm going to just brute force through all the vectors. 100% recall, which means it is highly, performant in terms of accuracy, but quite slow. No effect on memory. SQ is scalar quantization. So this is your bucketizing across 1 dimension. Low on memory, not as accurate. PQ, once again, scalar quantization, productized, even less memory, even less accuracy. Okay, so with that kind of overview done, let's go and get into the demo. Before I get into the demo, I'm going to cover what we're going to build today. We're going to look at 3 different code examples, and you'll notice that all the code examples are extremely similar, and the main difference is the data collection for them. And what we've done basically is we've taken Milvus and LangChain and OpenAI and put together some RAG applications that will work on 3 different languages. So there's 1 in French, 1 in Chinese, and 1 in Polish. So here is the QR code that you can scan. It is also available in the chat. And I will take some questions before we get into the demo if there's any questions that are pressing. So I see someone asking about AI agents and the cost intensiveness. Probably the LLM, probably the most expensive part. Okay, if there's no questions regarding the presentation, oh, there is, okay. What's the best approach when dealing with documents that contain multiple languages themselves? That is a really good question. I would say that what you can actually do, and I didn't do this in the example because this is a rather complex way to do this, is you could actually create an agent that will perform your embedding for you, and it will decide what embedding model to use. As long as all the embedding models are the same dimensionality, it will decide which embedding model to use based on the language that you are looking to embed in the document. Okay. In the embedding sense or retrieval, the Milvus collection side. As long as all your embeddings are the same size, the same dimensionality, you can compare them. They're comparable. If they're different, then you can't compare them. Okay, great. I think we can move on to the demo. Okay, let's make this smaller. I'm gonna need that in a second anyway. Okay, so let's start with a basic RAG example. I don't have a basic RAG example, do I? Okay. So we're going to start with looking at the Chinese example. And like I said, the most difficult part of this process of building these RAG applications is actually collecting the correct data. So what we're doing is we're building these RAG applications across a bunch of cities where we're going to ask questions about the cities. So we need to be able to scrape the city data from Wikipedia in order to give that data to the LLM via RAG to answer questions on. So we're doing Atlanta, Beijing, Berlin, Boston, Cairo, Chicago, Copenhagen, Houston, Karachi, Lisbon, London, Moscow, Munich, Paris, San Francisco, Seattle, Shanghai, Tokyo, and Toronto. Is anybody coming from any of these cities? I saw someone was coming from Seattle earlier. I'm also in Seattle, so go Seattle. If you're coming from any of these cities, let me know. I'm curious. So the first thing that we had to do for the Chinese version, and we also have to do this for the French version and the Polish version, although the French version was actually quite easy, you'll see. These are the English names of the cities. What we had to do is we had to convert these into the correct language. I had originally tried to just scrape them from the Wikipedia API. And if you do en.wikipedia.org, that's the English one. And so when I had used the English cities, I was able to scrape them all. But then when I put zh.wikipedia and I tried to scrape these cities, I just got straight like no data. So like I was saying earlier, when someone was asking about the multilingual stuff, like the most important thing is your data and your data collection. And so after translating all of these cities into Chinese, I then went and scraped them from Wikipedia like this. And I stored them into a example here that has all the text files and the Chinese cities. Okay. And then I built RAG on it. Oh, so this block of text is actually wrong. Okay. So for this example, if you would like to follow along, you can install PyMilvus, LangChain, sentence transformers, tick token. I don't think you actually need this one for this example, and OpenAI. And then you can get, oh, actually the standalone is in this file is in the GitHub repository. So you can just use Z shell or bash, whatever shell you're using, and just start the file and use start. So I'll you should run this because it takes a while to install. LangChain is a very big library. Sentence transformers is decently big. OpenAI is all right. So The first step that we're going to take here is we're just going to load our environment variables. And in this case, we're just going to load our OpenAI API key. And all we're doing is doing load.env and getting the API key. Next, we're going to go and get our LLM. And so for this example, we're just going to use the OpenAI LLM from LangChain. I believe this is 3.5 Turbo. And this is just the base OpenAI LLM. And now we're going to get the Hugging Face embeddings. So Hugging Face is a model hub that has a lot of embeddings. And we're also going to import Milvus, which is the vector store that we're using. And the first thing we're going to do is we're going to get our embeddings. So in this example, I'm using this specific embedding model, Townsview /PEG. And the reason I'm using this model is because if you go on to Hugging Face and you go look at MTEB leaderboard, you'll see that this is one of the leading models for the Chinese embeddings. And there are some other models that are better, but they are just a lot bigger and not better enough to justify using in terms of computational expense. And then we're going to import some things from LangChain to make this possible. So we're going to use the character text splitter. So this is how we split data, the chunks of data, right? So if we go in and we look at our data, we'll see that the data looks like this. And it doesn't make sense to embed this entire thing. And so what we want is we want to be able to split this up into reasonably sized chunks. And so that's where the character text splitter comes in. And then we've also got this LangChain document thing. And that's basically just a way to create entries into vector databases for LangChain. OS is just operating system. We use it for basic shell functions. So here, what I'm doing is I'm just listing out all these files so we can see them. So we can see that we have all these Wikipedia files. They're all .txts. And then I'm going to create this empty list of file text. And this list will eventually be populated by documents. And this is how we're going to insert into Milvus. So once we have this list, we'll go through all the files and we'll open up each file. We'll read each file, and then we're going to create a character text splitter, and we're going to create this with some sort of chunk size and overlap. And this is really up for you to play around with, but I find that 512/64 is a decent default. This is about, in English, this is about one paragraph, and this is about one sentence, one short sentence. And then once we have the character text splitter, we're going to split all the file text using the text splitter. And then we're going to go and we're going to loop through all those split texts and we're going to create documents out of it. So we're going to create this thing called page context, which is going to include the text. So this is the metadata that gets stored with your vector. And this is incredibly important for actually answering questions. And then we're going to also add the doc title and the chunk numbers. This just lets us know like which document it was in and where in the document it was. And you'll see that sometimes like there's pauses that we'll have, character text splitter has a set of tokens that it will split on, and it will let you complete sentences, which means sometimes you'll have larger chunks. And then once you have all these chunks and they're all vectorized, you put them into a vector database like Milvus. And so you'll see that we have that list of documents here called file texts. And we'll use embeddings as our embeddings function, and then we'll connect to Milvus this way. I have Milvus running on the local host on port 19530. That's what we did here with this standalone start. And then we'll give it a collection name. And so in this case, I've called this collection Chinese cities because these are the cities. Maybe it makes sense to call them like cities Chinese, but the choice has already been made. And then once we have that vector database and we've connected to it and we've inserted it, we'll use it as a retriever. So a retriever is just an object in LangChain that does some sort of, that allows you to retrieve data from the vector database. Now, the next part is where we come up with a prompt. And so prompts are the ways that we interact with LLMs. And in this case, we're going to create a chat prompt template. And we're going to tell it, you're an assistant for question answering tasks. Use the following pieces of retrieve context to answer the question. If you don't know the answer, just say you don't know. Use 3 sentences maximum and keep the answer concise. And then here, this is just like a basic RAG prompt. And then here we say answer in Chinese. And then we give it the question and the context, and we tell it to generate the answer. So the question and the context are both passed in as if you're using an F string in Python. And then we create a prompt template. And then we create the LangChain chain. So in this chain, the first thing we're going to do is we're going to give it context from the retriever. So notice this is a function. And we're going to take the question and we're going to treat the question as a function, as a runnable pass-through function. What that means is this is a function that just passes the text through. That's all it is. And then once we get the context in the question, we're going to put them into the prompt, which is how we fill in these values here. And then we're going to pass that to the LLM, and the LLM's output gets passed to string output parser. So in this example, I ask, what landmarks should I visit in Tokyo? And it tells me something in Chinese. I actually can't read Chinese, but it looks like you should go to Tokyo's. Yeah, I can't read this. Okay. And then if I actually, so this question right here is basically what should I visit in Tokyo? But I use Google Translate to translate it into Chinese. Oh, actually, we can totally just take this in Google Translate and see what it says. Translate. So this says, you should go to Fuji Hakone Izu National Park and Tokyo Skytree. And this probably says something very similar. But you'll see that actually, if you ask questions in Chinese versus English, you'll get different responses. And you'll see this in the Polish and French ones as well. And the reason that this happens is because the embeddings model is embedding something slightly different. And just because it's the question is similar in the languages, the actual text, the actual tokens are different. And so the embeddings model will produce different tokens. So I believe the answer for the Chinese one is, it says Tokyo Tower, Imperial Palace, and Sensoji Temple. So it doesn't even mention Mount Fuji, which is kind of interesting. Okay, so that basically covers the basics of how you should be building these kinds of applications. And now let's take a look at the French one. So you'll see in the, oops. Yes, okay. So let me just clear all these. You'll see in the French one, the only one we had to change was Beijing to Peking. This is the French name for Beijing. So that's the only change. And then here we used fr.wikipedia instead of zh or en. And everything else here is the same. And you'll see that we scraped all this text, and you can see that, hey, you know, all this text is in, oh, Moscow is probably different as well. Well, you can see that all this text is here in French. Okay. And now when we build the RAG application, this is also wrong. Okay. When we build the RAG application, all these steps are the exact same. So you can literally take this template and apply it to whatever data you want. The only thing you need to ensure is that you're using the right data. You can use this template and add whatever you want. The main things you need to make sure that you change are these embeddings. So you'll notice I didn't use the same embeddings model as last time. I'm just using the default Hugging Face embeddings. The default Hugging Face embeddings do decently well in French. Actually, the best embeddings for French is the OpenAI embeddings. I found that out later. And then change the directory that you're giving as your file directory. And you'll see, you know, this just makes sure that we're getting all the files here. And then we're opening them up. Same thing, chunk size, chunk overlap, still something you can play around with. Make sure that you're using the right file directory here as well. And make sure you change your collection name so that you get the right data back. And of course, in your prompt, you should tell it what you want it to answer in. So instead of answering in Chinese, we now want it to answer in French. And this is all the same. And so in this time, I've asked, tell me a historical fact about Karachi. And it will respond something like this. So let's see what's interesting about Karachi. Karachi was first mentioned in Theophrastus's History of Plants in 3rd century BC. It was occupied by the British in the early 19th century and became the capital of Sindh in 1839. In 1876, the future founder of Pakistan, Muhammad Ali Jinnah, was born and buried in Karachi. Well, I don't think he was born and buried in the same year, but there you go. That's an example of LLM hallucination. Now, if I ask the same question in French, it will give me a slightly different response. And this is once again due to the fact that the embeddings model here is actually going to embed your different responses differently. And this response will say Karachi is a city that was founded by the British in the early 19th century and became the capital of Sindh. It was an important economic center and experienced rapid growth. Notably thanks to its port, since the 1980s, the city has been the scene of ethnic and religious conflicts, and in 2012, it was the site of the deadliest industrial fire in history. And the last one is the Polish example. So in Polish, once again, you'll find that you have to go convert a lot of these city names. So there's actually a few ways you can convert these city names. There is a Python package called translate, and that Python package will directly translate some of these city names for you. The other way you can do it is you can go to, so in this case it's PL, you can go to the Polish Wikipedia and just put in the English name, and you'll get the you'll get redirected to the city name most of the time. And in this example, we do almost the exact same thing once again. All we do is change up our embeddings again. So here we found another embeddings model. And so once again, use the MTEB leaderboard, NTEB leaderboard. You can find the best embedding models, and you can pick your embedding models to from that leaderboard and go from there. And so this is the embedding model that is the best for Polish. And then everything else is just, changing the name Polish. And you'll see from the files that we're making sure that we're getting all of the right cities as well. And then we will just do the exact same thing here. We'll just change the name of the collection and tell it to answer in Polish and do the exact same thing. And we'll ask which sports teams are in Chicago. And I believe this is the Chicago Bears, Chicago Bulls, the Chicago Blackhawks, the White Sox, and the Cubs. And I think this should give the same answer this time, despite the fact that we asked it in Polish. But it's going to be a slightly different phrasing. And I don't know Polish, so I don't know what the phrasing is. It's going to be a different order. Is it different order? No, same order. Cubs, White Sox, Blackhawks, Bulls, and Bears. So yeah, there you go. This is the basics of how you build multilingual RAG applications. You take your RAG applications, you build it in the exact same way. The main difference is that you want to be able to ensure that you're using the right embeddings model, which you can find on the Hugging Face leaderboards to look for the best embedding models. You'll use a different embedding models for each language, or you can go and you can look for embedding models that do well on multiple languages. So the Hugging Face leaderboard has multiple languages options available, and in those multiple options, you can pick and choose the different embedding models that do decently well on all the languages and choose those models. So that's it. How do we know that this is the data that you input using RAG and not just the normal GPT answer? Because this is a really good question, by the way. The way that you would ensure that you're using the right answer is through this, the template. I guess like GPT is not very well known for following your templates, but the instruct tuned ones are. So what I would suggest is, if you don't believe me, I mean, I can just kind of like try to run it now. We'll see how it works, but you should just run it yourself and see like, hey, if I don't give it any of these texts, what will it say? So I don't have the exact example pulled up here, but I can go look for it. I do have an example of the model saying like, I don't have this in my context somewhere. But let me answer any questions before I decide to go and try to poke around in my workspace for these models. The other question is, didn't we use RAG to overcome hallucination? No, this is a misinterpretation of RAG. So RAG is not used to overcome hallucination. RAG is used to minimize hallucination. Hallucinations by LLMs are always a risk of using LLMs because LLMs are predictive machines and all they do is predict the next token. And there's no way to have zero hallucination. There's just no way. You can have 99.9, 99.99% of that's, it's coming from your data, but there's actually just no way to overcome hallucination. And if you think about it, that kind of makes sense because, you as a person, you hallucinate all the time. Like, you have every time we remember our memories, we're actually just creating new memories and calling it like, oh, this is what happened in the past, but it's actually happening in your brain right now. Does the LLM have to be trained in the language identical to the embeddings? And if yes, what about less common languages? So LLMs are typically trained across huge swaths of data, huge swaths of internet data. And they will have they will have access to all sorts of languages usually. Now, some LLMs are specialized to perform better in some languages rather than others. For example, the Qwen, QWEN LLM is specialized for English and Chinese. The Mistral model from Mistral, the French company, is specialized in French and English. I believe it can also do the other Romance languages as well. Italian, Spanish. I think it does those decently well. And this is a really good question is what about less common languages? This is something that people are working on right now, right? So the amount of data on the internet is in 55% English. Despite the fact that there's less than 55% English speakers in the world, 55% of the data on the internet is in English. And so less common languages, such as Arabic or Gaelic or, some other less common language are not languages that these LLMs have had exposure to. And so they don't have the same ability to answer and process those questions. So this is a really, really important example, a really, really important problem that a lot of people are working on. And I suspect that as we kind of move forward with technology, that this is something that's going to become more prevalent and more people are going to start creating data sets specifically on languages that are less common.
Last chance to get your questions in before we wrap up today's session. You can use the Q&A tool at the bottom or you can drop them into the chat. So Eugen, what was the hardest part of this project?
Collecting the data. Also getting the embeddings model to work. So I actually had to go through and test a few different embedding models because some of the embedding models are really big and I'm running on limited RAM. And actually this is probably a big problem for a lot of people is access to the right hardware is if you don't have 128 gigabytes of RAM, you can't run most LLMs locally. There are some tools out there that are looking to help people do that, like llama.cpp, LM Studio. There's a bunch of tools out there that are looking to help people do this kind of stuff. But in general, the hardest part is just hardware limitations and then collecting data. I fumbled around with the Chinese data for so long. I didn't even know why it wasn't working. And then I was like, oh, okay. I have to actually get the Chinese words of the sentences in here. And I can't just use English and have it automatically convert. Thanks, Rob.
Concerning the language agent, what is your opinion in the most efficient approach to actually detect language and let the agent do its job in choosing the embedding model, and what's the best practice in storing them in Milvus, each language in a separate collection? Question.
Yes, so great question. This is a very complex task. So, oh gosh. There are machine learning models that are able to detect language, and you have to run the model to detect the language, which is, once again, additional cost, additional overhead. But unless you know what language it is and you can tag it with the language, this is probably the most effective way to do it. Get the language, and then in terms of storing it in Milvus, you can only store vectors of the same length in the same collection. So I would suggest that you look for embedding models that can embed multiple languages, or ensure that all the embedding models that you're working on, if you want to be able to compare these different languages anyway, ensure all the embeddings models that you're working on have the same length. Otherwise, yes, you should store it in separate collections. And then when you store it in separate collections, you need to make sure that when you are working with this in production, that you are using the same embeddings models to query those collections, to embed the data to query those collections. So this is a very complex task that you're doing. And I imagine that we're going to run into a lot of bugs. Oh, great question. What are the best vector databases today? Well, I work at Zillus, so I'm going to tell you that Milvus is the best vector database. This is not really, my opinion is, if you want to ask this question, you should ask it to someone who works on LLMs or someone who works on, something other than vector databases. Because guess what? I'm going to tell you it's Milvus, and I'm going to tell you it's Milvus. I'm going to tell you why now. Okay, I'm going to tell you because Milvus is very flexible. You can use multiple different types of vector similarities, and you can use multiple different types of indexes, and it's super, super scalable. So if you go and you look at other vector databases, they don't let you use many types of indexes or many types of similarity metrics. In fact, this is one thing that I've been railing about for a while. Cosine similarity is super popular, totally useless. There was even a paper that came out earlier this year that was like, cosine similarity doesn't even measure similarity. And I was like, ha, I'm right. I've been talking about this for a while. It's an expensive metric and it's not very useful. So you can use different distance metrics and different indexes in Milvus, and that's what makes it really great. Emily, I can see your lips moving, but
Yeah, I was on mute. We have just a few minutes left, so if there are any last minute questions, we'll give you just a second. So type them in quickly. Oh, there's a request to share the paper on the cosine similarity note.
Let's see if I can find it.
If Eugene can't find it on the call, we can send it in the follow-up email with the recording later. Already got it.
Yep, I found it. I found it
Very
because
fast.
I've searched for it many times. Because guess what? I do not like cosine similarity.
Yes. A man of strong opinions. Any other questions from the audience today? Thank you, all of you who have joined us for the session. Hopefully you enjoyed it, learned a couple of extra languages along the way. Just going to stall for time for just a minute, but I'm not seeing anything else in the chat. So we'll let everybody out a few minutes early. You can get to your next meeting or head to lunch or wherever you may be in the world. Eugene, thank you so much for this session. It's been really fun, and hopefully we'll catch you all on a future webinar.
Thanks, Emily. Thanks, everyone, for coming.